Welcome to our senior capstone project presentation. Our objective for this project was to design, manufacture, and integrate an upgraded, fully automated thread stretcher machine sponsored by the company. The primary purpose of this machine is to ensure that the thread is processed with the exact physical consistency, which is critical for overall process consistency and reliable testing results. Previously, the existing process yielded thread with inconsistent lengths and frayed ends. This variation directly impacted repeatability, baseline measurement, and accuracy. To solve this, our team was tasked with creating an automated machine under $5,000 with a key performance metric being a thread length of 5.5 inches with a quarter-inch tolerance, a cycle time under 20 seconds, a minimum production yield of 85%, and a full compliance with the industrial safety standards. Every component of this machine was either custom machined or repurposed in-house. To remain within our strict $5,000 budget, our team heavily relied on the resource recovery from the decommissioned lines at the company. This strategy saved over $16,800 component cost. Key salvage parts include linear rails and carriages, pneumatic cylinders, safety relays, and our main structural base. Machine components were split between the Grand Valley State University and the company for manufacturing. For the in-house that was manufactured by the team, the student team machined the motor mounting plates, the linear rail adapter blocks, cylinder supports, and all Lexan enclosure panels to save labor cost. For the company, the high-precision components requiring specialized machining such as complex textured feed wheels, the main aluminum guide channel, the upper grip housing with precision duals, the spring guillotine blocks, and the custom base plate were fabricated by the company's tool room. So now we're going to go through the system's overview and the process flow, the in-feed subsystem. The process begins as is drawn from the existing humidity box spool through a 3D printed entry bridge. It enters a lock pinch driven roller system featuring an aluminum wheel with an indent, textured radius paired with an aluminum guide channel. An external lead screw allows the operator to easily adjust the high lead and pinch pressure during the spool changeovers. Gripping and tensions. An AC motor feeds the thread through the spring guillotine clearance block until it enters the gripping mechanism. A beam brake proximity sensor detects the leading edge of the thread and immediately halts the in-feed motor. A pneumatic cylinder clamps down with the flat surface grippers. Flat grippers were selected over tooth design during prototyping to eliminate material accordioning and keep the thread completely straight. Stretching subsystem. Once clamped, an electrical IAI linear servo motor pulls the grip assembly along the dual linear rails to achieve the exact target length of 5.5 inches. The static friction and the back pressures provided the in-feed wheel and channel maintain constant control tension throughout the stretch. The cutting subsystem. Once stretched, the cutting subassembly actuates a pneumatic cylinder driving a house guillotine blade. The blade strikes at a 45-degree angle against a suspended thread. Prototyping confirmed that this 45-degree shearing action eliminates the frayed edges entirely. Dispensing subsystems. After the cut, the linear servo performs an over-travel motion. The pneumatic grippers open, releasing the thread into a 3D printed funnel drop slot, assisted by an air blow-off line. The finished thread drops into an external tray for an immediate operator retrieval. Now for the control panel. The brains of the automated system is housed within the industrial control panel powered by Allen Bradley. The power distribution within the cabinets takes an incoming 120-volt AC single-phase power and steps it down with an industrial power supply to 24-volt DC to run the low-voltage control circuits, safety relays, sensors, and input and output modules. However, the primary in-feed driver motor is directly connected with a 120 AC supply for its main power. The main system controller is an Allen Bradley Compact Logix 5069 PLC paired with an Allen Bradley Compact 5000 digital input and output modules. The PLC executes a state-based lateral logic program. The process starts with rehoming to establish a 0 point for the electric linear servo. The motion timing, the sensor feedback loops, and the pneumatic solenoid actuations are coordinated through the PLC to ensure consistent operation. In testing, the control architecture reduced our cycle time down to a rapid 6.12 seconds, far faster than the 20-second specification requirement. Now for the safety, portability, and reliability. Safety and operational reliability were central to our engineering design. For the safety architecture, the machine is fully enclosed with a clear Lexan panel that offers toolless maintenance entry while protecting the operator. All access points are fitted with the PILS safety switches tied directly into a dedicated PILS safety relay. Opening any panels breaks the safety interlock, preventing machine operation. An e-stop button instantaneously removes power and halts all system motion in under 2 seconds. The entire assembly is mounted on a height-adjustable ergo base that moves up and down for operator ergonomics and can be easily relocated using a pallet jack. Portability. Flat pneumatic grippers and a 45-degree guillotine eliminated fraying, slipping, and bending, and we exceeded our 85 yield target. For future improvements, the IAI linear servo can be downsized to reduce overall footprint, and the dispensing air blow-off can be optimized for cleaner thread ejection. In summary, our team successfully delivered a fully functional automated thread stretcher prototype. Combining in-house manufacturing with the resource recovery allowed us to complete the budget under $3,160 in BOM cost, reduce cycle time down to 6.12 seconds, fully satisfy all quality, length, and OSHA safety standards. Special thanks to our sponsor, our faculty advisor, and the engineering workshop at Grand Valley and the company.